Is this working? Can everyone hear me? All right, sounds good, thanks. I'm Scott McCauley, and I'm here with Shuai. We're going to be talking a little bit about what Google's been doing with 48 volts over the last couple of years, or a few years. So anyway, welcome to the talk here, and if you have questions, I guess if you can save them for a little while, that'd be great. We're gonna switch over halfway through, so that's actually not a bad time for questions. But let's see, to start, basically we're going to be doing the 48 volt update, talking about Flatbed, which is a submission through the OCP rack and power track, and we'll also talk about switch tank conversion, and that's a piece of Google IP, DC into DC architecture that is open sourced and was talked about at APEC previously. So the agenda, like I said before, it's basically two parts here. We'll see if we can get through that in a reasonable amount of time. But the first thing is, where have we been over the last several years? And one of the things we wanted to talk about was, although in 2016 we announced that we use 48 volt architecture, it wasn't really until 2017 that we partnered with Facebook and released the OpenRack version 2 spec, and that was the one where 48 volts was added into the rack. And we're very enthusiastic about 48 volts. We're able to achieve the lower distribution losses with a very mature, well-developed telecom ecosystem that gives a number of maintenance advantages that we like, like a very fine-grained redundancy, so it's possible to hot swap out power, UPS, without bringing down individual servers in the rack. But maybe we can talk a little more about that. That's more or less an OpenRack v2 sort of capability rather than Flatbed or STC. But what we want to do is we want to, with the road ahead in 2018, we want to move into these payloads and focus on the payloads that we're putting in this 48 volt rack environment. And in that case, we want to build on the standards that have already been put together in the ORV, or the OpenRack version 2 spec, and talk about these two parallel, and I'm going to say complementary projects. Flatbed is a project where we're trying to take off-the-shelf servers and put those into 48 volt rack. Those off-the-shelf servers may not be native 48, but there's a rich environment, ecosystem of payload servers that we want to be able to get into a 48 volt rack with that efficiency and reliability and maintainability advantage that we see in ORV2. Parallel to that, we see these new non-isolated DC to DC converters as a potentially a very low-cost, high-efficiency way of making a very scalable and fast custom server design. So we've got Flatbed that's often for off-the-shelf. It may not be a high-volume optimized sort of application. And then we've got a different track that looks at highly optimized custom servers that would go as a native 48 volt payload into an open rack. So just to talk a little bit more about Flatbed, that's the off-the-shelf adapter kit. What are some of the motivations that were driving us and that we think are industry-wide motivations? Well, we definitely, like I mentioned before, we've got lots of proven 12 volt payloads in the industry. We want to be able to get lots of these different payloads into a single rack, and we want to speed the process. So Flatbed is, in a number of ways, more about speeding the process than necessarily providing the most highly optimized solution. It's about providing top line, providing a capability in the open rack which has the serviceability and reliability, and it's integrated into the large data centers in a way that may not be the case for other methods. So in the that released OpenRack v2, in that released Flatbed spec, I wanted to sort of talk about what were we trying to achieve with that, all the various items and sections in there. What we wanted to do is to be able to enable heterogeneous server deployments in a single rack, so both 48 volt native and 12 volt native. We wanted to be able to use any kind of conversion, be it an isolated 48 to 12 volt, be it a non-isolated, be it a 48 native, 48 to point of load. But again, I want to hit on the ease of deployment. What we really want to do is we want to be able to quickly adapt all sorts of different payloads that weren't originally designed for an open rack V2, get those into a 48 volt infrastructure that is easily maintainable with this, all the advantages of the rack level UPS and rack level power. So come down a little bit. That's what I just covered. And of course, we want to pick up the efficiency gains at high power levels through reduced distribution losses. So what does flatbed typically look like? Well, typical is a very difficult question to answer. There's a lot of freedom here, but the whole point of flatbed is to be a simple, easy, quick implementation. So what we're trying to do here is, with this top view of a server tray or sled, do a very simple mechanical layout, very simple thermal layout. If we need to give up on height or form factor or optimization, we're willing to do that to get this server into the data center, into that rack fast. And the way we do that is we use reusable components, and we use these reusable components, like I'm indicating here, and some of these air temperature sensors to shim between our generic server. This one looks a little bit like a Microsoft Olympus. I've been using this slide for a long time. And the Open Rack V2 infrastructure, which is the power vertical 48 volt bus bar. And we bring that into a horizontal bus bar on an IT shelf. And then we mate to that horizontal bus bar with a horizontal clip connector, very similar to the vertical connector. Take that power into the tractor PCB where we have DC to DC converters, feed our payload, maybe a server. That payload has to have a BMC with an SM bus that can talk back to the tractor and do consistent from implementation, from payload to payload, maintenance or maintain thermal environment, like fan speeds, and read consistent air temperature sensors, and also do consistent for the ease of software development, monitoring of power. Now, I should point out that there are many options to how you do the thermal control in here. You could, if your environment is such that you want to use BMC code off the shelf, you may find it easier to have the BMC directly control the fans rather than through the tractor. If your primary concern is to maintain air temperatures in the data center environment, you may find that it's easier to use OpenBMC on that BMC and control through a consistent fan control hardware interface on all sorts of different flatbed trays. So there's intended to be some flexibility there. As we go forward, what do we have? Well, we've been developing some initial prototypes, and we're bringing them up in the lab, Quanta, partner there. And we're looking at other form factors. These two are optimized for a couple different types of payloads. We expect them to have some level of optimization for different power levels, but the control and status is very similar across them. We've also got, you can see there's cabled options, there's different connectors options coming in here for that horizontal bus bar input. So anyway, to move on a little bit, I should move back here. So to do a simple implementation where everything's coplanar in a given open rack, it's going to place a few requirements, mechanical requirements, on the payloads. So we wanted to sort of publicize what do we believe are the most simple and easy sort of form factors and placements that we need in servers to fit into an open rack. Now, it's not to say that you can't have more complicated mechanical layouts. It just, this is what we want to emphasize as we think the easiest path forward for rapid deployments. And with this, we've got mechanical dimensions, a width, We're height agnostic, but we've got different depths that depend on what type of tray depth or rack depth you have. And of course, front to rear airflow. For serviceability, we've got all sorts of stuff coming out the front. And that means that we've got to have our PCIe slots at the front. And as a final detail, kind of want, if there's a given CPU with a reference design heatsink, it would be awfully nice to have that heatsink be, or the attachment and the keep outs be duplicated on all sorts of other payloads, so you can use off-the-shelf thermal solutions to quickly turn and quickly get these things into the data center. Likewise, there's some electrical requirements, and again, these are soft, but we think these help us getting these payloads into large data center environments where we have a lot of legacy rack infrastructure, and we have to shim this thing into our existing software. And of them, it's always easiest, fewer dependencies with no reserve pin usage. We need NCSI through the BMC. We need to control the tractor and do all this fan control and power monitoring. We also need what we're calling a clean SM bus header. And that means we don't want to get into address conflicts with anything on those payloads. So these are all sort of thoughts that make life easier. We can work around them if necessary, but it just makes life a lot easier not to have those problems. Again, we're betting heavily on OpenBMC, really like OpenBMC. We think that can make our support and bring up an integration task a lot easier across multiple payloads. And then we're trying to bin the number of different power varieties into a couple of varieties just to make it a little more simple, just to get a little more reuse across different payloads for just a few tractor PCBs or whatever you want to call that power and fan control PCB. Or it could just be a power PCB. I want to maybe go back a little here to some of the mechanical. Back on this slide, I had a little bit over here on the left. I occasionally get questions about what kind of bus bar, what kind of connector, and things like that, and I don't think I did a really good job originally talking about this with respect to how does this thing connect to an open rack? And the open rack V2 has the vertical bus bar that we normally see. This is the back of a Zeus sled right here. It interfaces to the, a Zeus shelf interfaces to the vertical bus bar. And it's got two contacts in there. Basically it becomes a powered carrier for the Zeus sled, which has a horizontal 4-pin connector. That 4-pin, that includes a short pin and a chassis ground. So we're able to get an early engagement of chassis ground, power, and then a short pin. What that gives us is just like any other sort of 48-volt networking gear or power supplies plugging in, you get a clean hot swap in and out. And that's, again, a serviceability play. We don't want to pull out a server out of a tray, have an ARC, and have a transient on that 48-volt bus shut down a neighboring server. So want to encourage the use of the short pin. And the short pin it's part of the Flatbed Spec. We need that to guarantee that we have clean and reliable operation and serviceability inside the open rack. And here's another couple of pictures of that. We've got a top view on the left, that horizontal shelf. We've got the vertical clip here. That's a two-pin nominally, and can be much higher current. And let's see. Going from here, I just had one little mention of compliance as well. You have many different data center environments. End users have to figure out what's going to work for them from a compliance standpoint. An open tray, like that one on the left, could be faster and easier to service, but there's a little bit more of a gamble in certain types of deployments, whether you can pass EMI, things like that. So that's open for the individual end user to talk about or to decide. And there are a lot of details in that Flatbed Spec that we just submitted recently. Didn't want to try and cover them all, but the basic idea is we're trying to put together a kit of components that we can use to bring all these various 12-volt existing payloads into our 48-volt racks. So at this point, maybe I wanted to ask if there are any quick questions, and then switch over to the second half, which is the complementary, okay, what do you do at high volume, and how do you quickly get a new custom server into that 48-volt rack. So let me switch to Shuai here.
Okay.
Yeah, thanks.
Thank you, Scott.
Yeah.
So we've covered most of the benefits of doing the 48-volt in the rack power distribution. So here I would like to give some more detailed comparisons on these board level designs, how we do how do we compare the 48-volt to point-of-load power conversion versus the 12-volt designs, and from different aspects. So here we put efficiency, density, scalability, and cost here. So for power supply engineers, we advocate for efficiency and density a lot, since this is what engineers really want to express their values. Here, there's other aspects they're very critical in the system design. That's the scalability and the cost. So let's look at this one by one. For the efficiency, today is a 12-volt systems, taking example from 12-volt to 1.8 volts Intel server and some other sub 1 volts other processors. The efficiency is pretty good. It's 95 to 96% for the 1.8 volt and 19 to 93% for 1 volt. And a good advantage of this, the 12 volt to point of load, is you have the best leverage of the power device technology advancement. It's less relying on the passive components, and all the optimizations in the power stage is dictating the overall efficiency performance. And if you look at the 48-volt system to point of load, definitely it's a more complicated design. Efficiency, if we optimize it, the efficiency is very good as well. It's 93, 94% for 1.8 volts we've seen today, and 90 to 92% for 1 volt. But the magnetic components, it's a big chunk of the whole solution. And the magnetic the design dictates overall efficiency performance. So that means you really have to spend engineering time optimizing those magnetics to get a good efficiency performance. And for density, the multi-phase system in the 12 volts, they keep increasing from year to year. We're seeing the current per phase is increasing, switching frequency going up, and the decoupling capacities in the processors can be reduced. So that's the density improvement on the 12 volt side. On the 48 volt, there's a variety of different solutions. So it varies significantly across architectures. Some of the 48 volt to 1 volt VR, they're very dense. Some vendors, they're doing a very good job. And some others, they're still catching up. But the key here is still on this magnetics. It's extremely challenging on the magnetic miniaturization. Another thing the next is for the scalability. So 12 volts multi-phase, we know that it's very scalable. You just delete adding phases, then you got the flexibility to support different power processors and specifications. And it uses standardized components and very fast time to market with very minimum engineering effort. And the 48 volt system to point of load, it requires custom components, particularly the magnetics transformers. It's longer time to market, and you often see there's a limited solution availability to support a variety of different needs. And the last is cost. 12 volt is mature, very low cost with the simplicity of design, simple components, and very wide availability in the market. And 48 volts power conversion on the motherboard is still higher cost today because it's more complex, more components, and more design complexity. Then we kind of revisited two-stage 48 volt 2.0 load architecture. There's a lot of discussion on whether we go with the single-stage direct conversion or two-stage. From my personal perspective, I really don't think it's a matter whether you're two-stage or single-stage, which one is better. It's case by case. So if you look at this two-stage, in the past, traditional ways to do the 48 volt to 12 volt regulated using quarter bricks or off-the-shelf bricks modules, and you get, that's a couple of years ago, you only got 96% efficiency on the first stage, and then you multiply the efficiency on the second stage. It's not that that compelling. But today, if we want to move further, move a step forward, we look at how we can optimize this two-stage. One decision we can do here is we do this first stage with fixed ratio unregulated. If it's fixed ratio, the topology itself minimizes the dependence on the magnetics. You shrink the magnetic component size, and you can easy to achieve softer switching for unregulated designs. And the density is also, higher density is also easier to achieve. And now we are doing our switch tank converter technology for the first stage. That is a very high density switch capacitor derivative topology. And we open up this IP to the industry. And also there's other fixed ratio converters that provided by some other vendors in the market. So basically this first stage unregulated, if you do this higher power centralized bus converter and then supply the power to the second stages, the higher power you do for the first stage, you get lower cents per watt for the first stage as well. And a good thing for the second stage is we are able to leverage industry's continuous improvement and the ecosystem of the multi-phase VR technologies for the best optionality and total cost of ownership. So the two-stage architecture, we think, it consolidates 48 volt and 12 volt ecosystems for the motherboard power designs to meet the future demand, and helps people to have a smooth transition from the 12 volt to the 48 volt system. So here we show this STC topology. It's a very simple switch capacitor derived. Here we have the main FETs, the 4 FETs showing on the top, and the 6 FETs on the bottom. They are synchronous rectifier switches. They're all low voltage switches. And the first and the third branch, they are the 2 resonant tanks using the very small inductor and class 1 COG or U to J capacitors for the resonance. And the center flying cap is a filtering traditional class 2 material capacitor. And this is a brief, it's an overview of the, helps you to get a feeling about the size of this converter. 600 watt is about 40 millimeter by 22 millimeter size using all standardized components. So here are the features. Have high efficiency and density with the softer switching and the high energy density of the capacitor components. And basically, it's just try to minimize the utilization of the magnetics. It achieves very fast transient response with very minimum energy storage components in this topology. And because the inductor is small, so you can do very high peak power, so you're not gated by the saturation current of the magnetic components. And it uses low voltage FETs with the very good figure of merits in the market. And it also solves some of the fundamental limitations of the traditional switch capacitor topologies. That is how do you softly charge those flying capacitors and softly discharge those capacitors. So that's why we put the inductors here, and the soft charging and the soft switching is always guaranteed. So this also helps us to have a tightly controlled resonant operation over wide range. It's not sensitive to any capacitor tolerance and board parasitics. So with this tightly controlled resonant operation, we are able to control the impedance of this converter, output impedance. In that way, you can do inherent droop current sharing for parallel operation. So that helps you to scale up to higher power. And for the scalability and the cost advantages, first, this topology can be easy to scale for different ratios. So here, the example here is 4:1, and we can also, by adding more branches, to get 5:1, 6:1. Depending on the specific application requirement, you can optimize the ratio. And also the power level is, you can do multiples in parallel to support higher power. And it's using standardized components, so you don't really need a big effort in this custom design, custom component. And that also saves the qualification effort and time to market. It's low-cost on-board chipset solution with standardized components. So with this approach, you just use off-the-shelf silicon components, capacitors, inductors, and you put it on your motherboard, and you're done. It's very simple. It's low-cost, discrete components. And we open up this IP to the power industry, so everyone can use this topology, can design, develop IC silicon devices based on this. And this also gives us strong leverage on this second stage 12-volt VR technologies. We did an evaluation board demo here. So to make it work, it's fixed ratio. We add in front end startup and protection circuit. Here we put a buck converter, so it only operates, it only do the switching operation during startup. Once it's reached steady state, it's 100% duty cycle with 99.9% efficiency. And this buck can also be replaced by, for example, the eFuse hot swap device for the startup and protections. And STC powertrain is in the black box, the blue box, and we showed the capacitors, FETs, and inductors here. And the controller driver ICs, they're in the yellow box. So those devices can be potentially integrated. So overall, we can achieve a better power density in the future. Two experimental waveforms showing here. So the first one is showing the resonant operation. The two resonant flying capacitor ripples is showing here. So it's 90 degree shift from the current. So you can derive from this waveform, knowing that it's a zero current switching. And because of the softer switching, it's very quiet on the switching node. You don't see any spikes. And it's a very fast transient response with a droop, inherent droop on the output. And the efficiency we got here without the bias is approaching, without accounting the bias loss, just the powertrain, is approaching 99%. And counting everything is peaking 98.5%, and then full load 97.6% efficiency. So I'll let Scott to conclude this presentation.
Run up here, yeah, okay. So let me see if I can remember that. Anyway, to summarize, so yeah, we wanted to talk about, we've got multiple ongoing projects and programs to try and address different 48-volt rack and power needs. And there is some overlap between the two, but wanted to basically present those and get feedback and questions from the audience. Oh, thank you for reminding me to turn on my microphone. I don't know. Am I feeding back or anything? Okay. Turn this off. So any questions? Yeah.
Hello, everyone. Thank you very much for presentation. And the next year, this is the second year where we are looking for very good Google direction to 84 volts. If you're coming back to the one of the slides where you try to compare 12 volt infrastructure and 48 volt infrastructure, yeah?
Yes.
I think it's more than 50% people in that room after looking at numbers say why Google going to 48 volts, because from a point of load perspective, from 12 volt to target volts for particular ASIC, for example,
Yeah.
it's much more efficient, yeah. And that 1% efficiency, it's not so small amount of that.
Yeah, I guess if to understand the question correctly, here, I'm going to give you that.
So I think your questions
Yeah.
about this efficiency, lower efficiency for the 48 volt system compared to 12 volt. Yeah, because this is on the motherboard only. So if you just look at the motherboard, you have higher step down ratio for this 48 volt to 1 volt compared to 12 volt, right? So the efficiency is lower. That's okay, but the majority of the savings is on the rack level, and I think there's a lot of other presentations already addressing the benefit of this saving on the front end, AC to DC, and then bus bar in the rack. So that's the majority of the benefit.
Yeah.
Where they're coming from.
Yeah,
Yeah.
I want to back that up and say, by moving the high voltage to further out, that allows us to do UPS and distribution at the rack level with 48 and lower our distribution losses. And we think it's probably like maybe a 1%-ish, kind of gain in distribution. Yes, they're all very small. Yeah, and then I want to come in and make a plug for. With reduced distribution losses, it can make it easier to decide to do your redundancy at the rack level rather than at the server tray
I think
level.
another point is how much power you want the rack to support, right?
True.
So there's a presentation this morning from Huawei, and they did a very nice study. If you are doing a rack less than 15 kilowatt, it's 12 volt is fine. But if you're going higher, above 12 volts, that's the power loss on the 12 volts distribution increases exponentially.
Yes, you're absolutely right, but not so many data center, and you designed an old one capable to take off, for example, more than 25 kilowatts. And this is 70% of data center not able to do that. And of course, this is a visible, sorry for that, I try to be open because it's open community. This is a visible, like a game of the big guys who is trying to invest $1 million for find a reason for going to 48 volts instead of 12, because infrastructure for 12 already prepared. DC to DC from 12 to point of load, very well tuned. It cheapest more than 3 times. We have that analysis, 3 times than what we call doing is, yeah? And losses potentially available in boost bar, in 12 volt boost bar instead of 48 volt, it's smaller than 1%, yeah? It's a question is how many people demand of that?
Right. Oh, it's good. It's yeah. Oh,
I think the one reality we're seeing is this power increasing, right? It's increasing very fast on all this data center machines. So a couple of years ago, your server is still talking about like 160 watt per socket, CPU socket. And today you're seeing a lot more 300 watt designs and processors, right?
Yeah, you're absolutely right.
Then if you still stick with the, let's say, 12 volt infrastructure, the rack, you're probably seeing a challenge of you have to remove some of the machines from your rack. You cannot fully populate your rack.
It's a problem is to take off enough heat from the rack level, yeah? And if you looking for some trends about immersion cooling. It's maybe after 2 years from now, we are sitting in the same room and discussing about trend. I think more and more data center go into immersion cooling for one phase or two phase, instead of try to using air for take a 35 or 40 kilowatts from the rack.
It's just still like immersion cooling will not solve your efficiency problem, right? It's just solve your thermal problem.
Yeah, it's a solve.
Yeah.
A lot of power we can save for fans, for example. And this is the losses instead of number of the money what need to invest on that. It's maybe not comparable. Maybe it's a private opinion, but
I think that's true. There will be different trade-offs for different types of installation, and for the very high power ones, we think the 48 is more of a sweet spot for a number of reasons. Yet at the same time, we expect 12-volt payloads to be around for a long time, and we need to support those in a consistent, data center environment. So.
Yes, of course, but especially for open power product, where which Google using and which using rack space, big guys decided to use in 48 volts. For many customers who have 12 volt infrastructure, not able to use in that.
I see.
Anyway, this is a gap.
Right. Yeah. So we need the other adapter.
Yeah, my name is Jiang. I'm actually from Power. The same team as Shuai. I think very good comments. If we just to add a few quick comments here. Actually, that's one of the you mentioned, right? If you look at the comparison between a 48 volt and 12 volt, especially, I think since we joined OCP like 2 years ago, we actually heard a lot of feedback about, hey, your DC-DC portion is too expensive. It's like a ecosystem. You don't have too much choice there and things like that, right? And I think if we kind of come back to this STC stuff, it's really, the goal is we're actually trying to make effort to kind of improve in this area. And I heard some numbers that you just mentioned. DC-DC may be 2 times or 3 times more expensive. And this effort, if we come back to this STC, is actually to make it, instead of 2 times, we make it very close. So that's kind of the goal here. Just to kind of emphasize, we may not be the same still. There's still gaps there. But we think this is extra effort we are trying to make and to kind of make some improvement here. And hopefully, I'm actually very happy to see, like, when I sitting in this OCP, I have seen so many intentions from industry about 48 volt. Different suppliers come out with several different solutions already. You actually seen, like, over the last 2 years, I have seen a lot of progress has been made, and it's the timing thing. And I fully agree with what you made.
But if you are concentrated 2 years, concentrated to another, for example, ways, maybe this much more efficient than try to invent bikes, something like that.
Agree. Like you can also make continuous improvement in the other area if you put effort, right? That's your comments, and I fully agree with that. And I think it's again, this is like we emphasize. This is kind of an open forum, and it really depends on your application and how you see this one, whether it makes sense for you to kind of making the adaptation, right, from 12 volt to 48 volt. And I think to add it to this flatbed session is actually a kind of a partner effort. Yeah. We also seeing like, we are the one who's doing 48 volt, but at the same time we are struggled a little bit of getting a payload, right, a diversified payload into our system, and that's why actually we came out with this flatbed concept. And we kind of expecting maybe the industry sees similar things, especially during the transition time. And that's why we kind of made a contribution back to OCP, and hopefully that can help a little bit of the transition.
Give some guidance. It's like what our problems are, what our struggles are.
Yeah, big animals, for example, like Google, of course, can push industry to good direction, but need to keep in mind maybe it's the wrong direction.
Sure.
Well,
it's not for everyone. Right?
Not for everyone. Yeah, exactly. Good comment.
Thank you. Thank you very much.
Thank you.
Yeah. I think Ed's.
Okay, so I have some questions because I'm trying to understand stuff. And so I don't know if I got it right.
Ah.
So I want some clarification on that. Okay, so when I look at this table up here, I think that that's a kind of a problem statement. And the problem you're saying is that's a picture of today's systems, not the stuff you presented. And so if you look at the top row, that's what you're trying to fix or improve. And so I guess the question is, at the end of the presentation, the efficiency isn't 90, you've got different numbers at the end, right? So if you were to draw your conclusions in those same boxes, what would the first box say? Once you have the switched tank, capacitor tank.
It's similar, right?
It's the same, so you're not changing the efficiency?
I'm not changing the efficiency.
Okay.
Yes.
So the efficiency, when you're all done, this is an early view graph. So when you're all done, the numbers in the first box don't change.
Exactly.
So
Okay, the numbers in the second box, or the statement in the second box, do those change?
yeah, so a lot of problems not only for efficiency and density, like I mentioned in the presentation. So it's about scalability, cost. So we want the benchmark to today's efficiency
Yeah.
that we already see, right? And then this solution, you meet this, right?
So they're the same.
Yeah.
Okay, so
And
no
then
change in
the
the first box.
density-wise,
Yeah.
it's more about a question how you understand the density. So actually, if you look at the motherboard design, the power components density, you really have to look at the density at the processor side.
Okay.
If you have let's say you have a 48 volt to 1 volt converter, you can do different conversion stage, right? One stage or two stage,
Right.
or you partition the converter to two pieces, and one place the further away from the processor, other is close to the processor.
Right.
They make a difference.
Yes.
Yeah.
Okay, so
Please keep in mind, server is not mobile device. It's not mobile phone. We need to focus on density only.
Sure, yeah. I mean, I think, is it fair to say that with the proximity and the size, we're worried about like the IR losses at 1 volt? So we,
okay.
okay.
Okay, so so I'm just trying to understand this view graph. That's all I'm trying to do here. And so the second box, it says density. I think what you're saying is that the 48 volt from today's to what you presented is largely the same, but you might have closer proximity at the processor. Is that right? Or is there a difference? Is the second box the same or different after the work you did?
So if you do everything, let's say you look at today's
Right.
48 volt to
Yeah.
1 volt solutions, there are many different designs, right?
Yeah.
Some of those, they can fit very well,
Okay.
but some of those, they are not very dense, right?
Okay.
If you put that right next to the processor and you consider the same amount of current that VR can
Right.
deliver, it's larger size than this 12 volt multi-phase VRs. It's still the case.
Okay. So if we look at scalability, I'm just trying to go across those boxes and understand the difference between what you stated was today's and what you presented. So in the third box, scalability, you're working on not having so many custom components, right? So you're proposing standardization. So you're saying you're going to see improvement in the third box?
So the scalability is like one thing is here is if how long you have to spend on optimization of that custom components, right? A lot of time we see if you involve a custom components, the right way is you give the spec to your vendor a long time ahead
Right?
of your project start.
Yes.
But a lot of cases we don't have that luxury.
Right.
The project just happened and we want to deploy as fast as we can.
Yeah, so
So
But I guess the point of this presentation, especially this slide,
Yeah, that's
is actually what you can show here. You can see here is like we emphasize actually there's a lot of benefits of doing 12 volt, especially for the 12 volt to point of load area.
Yep.
And one of the STC motivation is actually trying to do a very efficient, very high density second stage so that we can leverage all these 12 volt system benefits.
Okay.
That's the point of this one. So I think in the past we have seen several vendors trying to bring a 48 volt to point of load solution with very customized design.
Yep.
And that's kind of a limitation from different payload suppliers, and they see these constraints. And we see the same thing, right? We see 12 volt to point of load is easy to design, is very easy to scale, and cost is very effective. And so we are kind of shifting our direction and trying to drive a good solution on the first stage so we can leverage all this 12 volt ecosystem here. And so that's really the point of this slide.
Okay, so you're mostly attacking the cost box and seeing improvements in the cost in a two-stage system by lowering the cost of the first stage.
Yes.
Okay, and you're trying to standardize that and get better scalability.
So the idea on that boxes is that, yeah, so the thing is that if you're asking, is there more headroom on the first box?
Yeah.
Yes, there is. So this is what it is today, but on the first one, it takes a lot more custom design and all that stuff, but you could see more headroom on the first one. But based on what analysis and scalability, meeting lead time, all those things and so on, that's where the second approach comes in and addresses those concerns.
Right. I think we are kind of talking about two things here, right? One is what the focus here is on the board level, DC-DC, and how we do 48 volt or 12 volt to point of load. And then the other point I think we are talking about here is, hey, you see the benefits of moving to 48 volt. And that's not really part of the payload portion. It's actually you have to look at the whole system level from AC. Exactly. So I see this is kind of two topics, right? And I think it's easy to get confused when we kind of mix them together, and that's the way that I see it here.
Okay.
But thanks for your comments. Great.
I was looking for before and after, and this was a before, and I was wondering what is after. And it sounds like it's mostly cost and standardization and scalability.
Yeah. Yeah. You get that. Yeah.
Yeah. Yeah.
Yeah. And that's actually the effort that we put. STC is trying to kind of leverage the existing solutions, and that's the point. That's addressed.
Yeah, thanks.
Yeah, okay.
Thanks, Shin and Mobashar, for helping fill out.
Jump in.
All right. Any other questions? Yes.
Yeah, I don't have a question, just have a comment. I think it's great that Google can list this way, like in a very transparent way,
Yeah.
and being open to kind of self-criticize, say we lead for the AWOL, but there's all kinds of cons here, and here's the way we kind of trying to work around it while still enjoy the efficiency and distribution and the AC to DC. So no question, the
Great.
comment.
Okay. All right. Yeah. That is part of our goal. It's to sort of publicize. Hey, here's areas we're working on, and if industry can help us, we have limited resources. There's so we need to partner. Yeah.
So I have one quick question.
Yes.
Yeah.
Yeah.
So the efficiency improvement. So let's just say you are using a 48 to 12 bus converter versus your STC approach, right? STC approach seems to be more efficient, right? A little bit, maybe 1%.
Yes. Yeah.
So that is happening due to the fact. I mean, I have a conjecture.
Well, why is it due?
Yeah. So I have a conjecture that you were probably not forced to use a 100 volt device like 40 to 8, and you were using all low voltage and kind of more switches, but better switches, right? Is that the reason, you think?
Yeah. Let's give it a try.
Yeah, so you see that topology actually is multiple current paths in parallel to deliver power, and each path they consist of a couple of low voltage devices.
Right.
So it's with lower voltage. I think the key is low voltage. You can switch faster compared to the high voltage switches, and that enables the higher density. And also,
you are not switching that fast, but still, I would say the RDS on will go down by significantly. Even if you keep
RDS on goes down, but I would say your current also goes up, right? So it's a low voltage device, higher current, or high voltage device, lower current. So that's
no. I'm saying that everything remaining same. Your current does not go up. You cannot do multiple scenario. Just keep the same scenario, same output, same input power, same output power. So 48
Yeah,
volt
I mean
or
the
12
current
volt out, same power, right?
I mean the current in each device. So
You have 6 switches versus 2 switches. You can do a half bridge with the 48 to 12 bus converter, right? Easily. I mean, that depends upon your topology choice.
Yeah.
But overall, my point is that I do low voltage switch for a living, so I know for sure that your RDS1 can go down by 5 times.
yeah, you
Use
think
a
about
25 volt
so
MOSFET.
let's say you have a
100 volt.
case, you have you use 180 volt FET
Right.
to carry the 10 amp current,
Right.
and you have 25 FETs, 25 volt FETs carrying the same current.
Right.
So if we just look at the I square R losses,
Right. Right.
you may not be that bad with the 80 volt FET, but I think the advantage here is the low voltage FETs can allow you to switch faster.
You may not need 3 FETs because, for example, in higher voltage FET, you sometimes have to do paralleling to get the same current, right? But low voltage, you get the same resistance with the same footprint. I mean, you get the same RDS on. You
Yeah,
can just replace 2 switches by 1 switch.
Yeah, it's case by
Effectively.
case, yeah.
Yeah. I mean, total switch count goes up, so you have more BOM cost. But okay, thank you.
Okay, anything else? All right, thanks.